The normal curve is one of the most important topics that we'll cover in all of this course. And later on, when we get into different topics, we will use the normal curve in many of those topics. There are properties that are true of all normal distributions. And the first thing is they are symmetric around the mean. Okay, and they have this bell shape to them. Okay, so if you were to draw a quick sketch of a normal curve, okay, this is what they mean by a bell shape. The mean, median, mode are all equal to each other and are located at the center of the curve. So right here would be your mean, median, and mode. The third thing is a little bit different for us now. The total area under the curve is 1. The way to think about that right now is think about percentages. If you had 0.90, you would think about that as 90%. So if you converted a percentage into a decimal, 90% is 0.9. Well, the 100% would be 1. So you want to think about that area under the curve being, the total area under the curve being 1. Think about it as 100% of the data lies under the curve. Okay, the fourth thing, the curve approaches but never touches the x-axis. Okay, so on each end, right end and the left end, the curve approaches but never touches the x-axis. Okay, the x-axis is called an asymptote to the curve. The fifth thing is the empirical rule applies. And the sixth thing, the distribution represents a continuous random variable. Okay, and later on we'll get into what each of those mean in 5 and 6. Okay, so as an example, suppose the wait time on a Friday night at a busy restaurant is normally distributed with a population mean of 40 and a population standard deviation of 6. So mu is 40 and sigma is 6. Draw the distribution and label the axes. So what we're looking at here is just to kind of introduce what the normal curve is and how to label it. So we're going to draw a shape like this, the normal curve, a bell shape, and then we're going to label the mean of 40 and the standard deviation of 6. We're going to label that along the x-axis. Now I already have this drawn out, so it's a little bit neater than what I could do live. So you draw the bell curve. 40 is right in the center, that's the mean. And then you're going to, generally, when I say to label the axes, what I want you to look at is going 3 standard deviations above and below the mean. So the first standard deviation above the mean will be 40 plus 6, which is 46. 2 standard deviations above the mean will be adding another 6 to get you to 52. And then 3 standard deviations above the mean will take you to 58. And then when you go below the mean, 40 minus 6 will give you 34. Subtract another 6 to get 28. And then subtract another 6 to get 22. Okay, so that is what the distribution will look like for this example. Okay, we previously looked at z-scores, okay, and the normal curve is going to make use of these z-scores. And recall that a z-score tells us where a data value lies relative to the mean. So the formulas to find z-scores, if you have a sample, you take the data value minus the sample mean, divided by the sample standard deviation. And if you have a population, you take the data value minus the population mean, divided by the population standard deviation, sigma. And we're going to round z-scores to the nearest hundredth. So find the z-scores for the following wait times. Okay, and this is something that we should have looked at earlier in the course. So if x equals 52, you're going to plug 52 into your z formula for x, because that's our data value. Subtract the population mean of 40, and then divide by 6. So take a minute and pause the video if you need to, and go through and do each of these, A, B, and C, and I'm going to put the answers up right now. but I want you to try these and pause the video until you're done. Okay, so there's the answers. So a wait time of 52 minutes is 2 standard deviations above the mean. A wait time of 34 minutes is 1 standard deviation below the mean. And a wait time of 50 minutes is 1.67 standard deviations above the mean. Okay, on the next page, we can also transform the x-axis into a z-axis. Draw and label the z-axis on the diagram in number 1. Okay, so what we're going to have here is you draw the normal curve. Okay, I'm just redrawing it here. Instead of putting x, the data value for the wait time, on your axis, we're going to put z. Now, I had already mentioned that when you look at labeling this x-axis, okay, so in this one we had x, 46 is 1 standard deviation above the mean of 40. 52 is 2 standard deviations above the mean. 58 is 3 standard deviations above the mean. So in terms of a z, remember that z is telling us where the data value lies relative to the mean. So a data value of 40, or a wait time of 40 minutes, is where the mean is. So how far away from the mean is the mean? Well, it's 0 away from the mean. So the z-score for 40 minutes would be 0. For 46 minutes, well, isn't 46 minutes 1 standard deviation above the mean? So the z-score for 46 minutes would be positive 1. Okay, for 52 minutes, we actually found that down here in 2a was a z-score of 2. Okay, so what I want you to see here is on that second page. Okay, when you label your axes, you can look at it in terms of a z or an x. So a z-axis tells you the number of standard deviations you are from the mean, and the x-axis in this case is telling us your wait times. So these x and z axes represent the same thing, but in a different way. Okay, so a wait time of 28 minutes would be 2 standard deviations below the mean. So that's how you want to look at that. Now, why we're doing that right now is not obvious, but we'll get into that in another video. Okay, what I want you to remember is that random variable x, so in this case the wait times, is 1 individual wait time. The z-score for that x value, okay, so the z-score for that wait time, tells us where that x value or wait time is relative to the mean. So again, a z-score of 1 tells you that a wait time of 46 minutes is 1 standard deviation above the mean. Okay, so x represents an individual wait time, and z represents where that wait time is relative to the mean. So it's very important to understand that, because we're going to use this normal curve many times in much of the content going forward.